Okay, good evening, everyone. Hope you all are doing well. Uh, so, hope you got the results for quiz two. No, I'm not sure about the results, but the solutions, and I hope quiz two was okay. And I hope you all are preparing or prepared for the OPP. All right. So, one thing is you can see a some mock questions have been released on the portal. Uh, Yeah, so if you have, uh, did you all get a chance to go through the through the mock OPP questions? Yes, no, you can reply on the chat. The mock for programming exam, there's a tab on the portal. Were you able to go through the questions? Okay, not yet, not yet. Okay, so most of you are saying not yet. All right. And okay. So then let's keep it open. Let's keep it as an open session. Uh, you can ask questions. If maybe we can discuss the uh, mock programming exam questions. Is that okay for all of you? Or do you have any other specific doubts which you want to ask? That also can be done. So I will leave the session open. Uh, So either we can take the mock programming questions now, or if you have any other general doubts, we can take that first. Okay, so I've got three, four responses for mock. Others also, if you want mock, uh, we can do that. Snehil is asking about the Ford-Fulkerson algorithm. Okay. Snehil, any specific doubt on the Ford-Fulkerson algorithm? Oh, sorry. Yeah. Uh, okay. All right. All right. Are others facing the same difficulty in the Ford-Fulkerson algorithm? Okay, so why don't we do one thing? Maybe let's start with the Ford-Fulkerson algorithm and then I will go on to the mock questions. So, if others are familiar with Ford-Fulkerson, I would suggest just go through the programming questions, right? Meanwhile, and I'll just explain Ford-Fulkerson and then we can go to the programming questions. All right. Okay, is that plan okay? Yes, no, yes on the chat. Ford-Fulkerson followed by mock programming questions. Okay, you can reply in the chat, yes, no. All right. Okay, let me just start sharing my screen. Okay. Okay. All right. So this is part of week 11, right? And as you all know, so we started week 11 with linear programming. Then we moved on to network flows. And then there were other topics about complexity, reducibility, all of those things. So network flows is the problem is simple, right? So what does it talk about? So you have a source S, right? And you have a sink, like your things are moving from S and it is moving to T. And you want to find what is the maximum possible flow, right? Which can flow from S to T. Okay. And obviously, it is constrained by how much can flow from S and how much can reach T, right? So, for example, here you see that S can only push, if you say, like 3 units of something plus another 3 units of something plus another 3 units. So 3 plus 3, 6, 6 plus 4, 10, right? And here you can see that it can receive only 2 plus 5, 7, maximum 7, right? So no matter uh, how much you push, right, you are constrained by how much S can push or T can receive, right? And here you can see that although there are 10 units between A and B, you cannot push that much, right? And another constraint is that whatever enters, right, should be equal to whatever exits, right? It's a very intuitive thing. It's a normal conservation law, right? The whatever enters, the same should nothing is stored in a particular node, right? So in this case here you can see that 3 is entering and 10 is entering A, but A just outputs 2 units. So at the max, it can only receive up to 2 units, right? Okay, so I hope the problem is clear. Now, yeah, so what we have to do is find the maximum possible flow in a graph of this form, which has a source S and a sink T, right? That is the problem. The problem is to find the maximum flow possible in such a graph, right? And that is where we use the Ford-Fulkerson algorithm. Yeah. So right. So yeah, let's take a simple example. No? So this one, right? So uh, okay, in the chat for those of you who don't know, right, or who are just learning, uh, what are the possible uh, flows or what are the possible paths from S to T? Can you tell me? Just ignore the numbers for now. What are the possible paths from S to T? You can reply on the chat. Okay, Snail is saying SAT, SBT, SABT. Okay. SAT, SBT, SABT, right? Are there any other? Yeah, SAT. All right, very good. Right. So here you can see SAT, that is this, right? And we see that a maximum of 1 plus 1, which is 2. 2 units of flow can flow from S to T. SBT is another path, right, where you have, sorry, not 2, I'm sorry, flow of 1, right? You can flow 1 unit across, and you have SBT, which is another 1 unit, right? And you have SABT, which is another 1 unit, right? And you will notice that you can take some paths together, right? So in this case, you can take the path SAT and SBT, SAT and SBT, right? And it doesn't violate any of the conditions, right? So the flow will be S to A, and then A to T, and S to B, B to T. It takes 1 unit here, 1 unit here, 1 unit here, 1 unit here, right? So we can combine these two, and hence we can say that the maximum flow is 2, right? Whereas if you take this, if you take uh, if you take this path, take another color. So if you take this path, okay, you will realize that uh, a flow of 1 unit goes from S to A, that comes from A to B, and then again it goes from B to T. Okay. Now, so this link is used. Now, there's no way I can use this link, right? Why? Because if I need to push something from here, right? So 1 unit is already going here. I need another unit here, but my incoming edges, the weight is, I mean, the flow is only 1, right? So in a way, this path, right, this red path is a non-optimal path, right? It doesn't give the maximum flow. Whereas the blue path, right, it gives the maximum flow. Okay, is this clear? Is this much clear? Any doubts in this? All right. So now the question is, how do we come up with this maximum flow, right? That is the question and that is what the Ford-Fulkerson algorithm helps us to do, right? And what it tells us is, okay, uh, what the algorithm tells us is, you take any path, you start with any path from S to T, okay? But as you take a path, right? So this is somewhat similar to that dynamic programming approach. We at the start, we really don't know which path will give us the maximum flow, right? Or which set of paths will give us the maximum flow. We will try a path, we will make some changes, and then we will see if we can add more paths to it, right? If we can, we continue, otherwise we stop, right? So that is basically what is happening. So let's say we follow this path, okay, S, A, B, T, right? The non-optimum, right? Let's say we follow this. So what we'll do is we will take this path, S, A, A to S to A to B, and then B to T. Okay, all right. So now once you do this, right, what we will do is we will create something known as a residual graph. Okay, a residual graph is nothing but it tells me that, okay, now okay, I'll just change this also. So now since 1 unit is flowing from S to A, right, I will change this 1 to 0, right? I'll change this 1 to 0. I'll change this 1 to 0, which tells me that, okay, now I cannot push anything more from S to A. Okay, is that clear? But along with that, I also add residual edges. Okay, what I mean by that is, I know that there is a flow from S to A. So for every such flow, I add a backward arrow, which is the total, how much flows, the total capacity minus plus how much is flowing, right? So here we see that we pushed one unit from S to A, and what the residual graph is telling, okay, that means that there is something which can go from A to S1. Okay, is this point clear? Any doubts here? So for each edge in my path, I create a residual edge as well, right? So this will also be 1, and this will also be 1. Okay, so Snail is asking, so the residual edge will have the same weight. Okay, so that actually depends. So for example, here in this case, maybe we'll see the example later. So so it's like whatever is pushed, right? Uh, in a way, it tells me how much how much was pushed, right? And how much should I so if I were to undo that, right? How much uh, how much flow would come back in the other direction? All right, maybe we'll take the other example and then we'll see what can be. So weight S minus A is equal to weight A S A. Acha, S A. Right. Correct. So S A is actually 0 now, right? Because we have already pushing 1 unit and we are taking AS as 1 now and SA is 0 right now. Right. So I think maybe let's see this. Yeah, so maybe. So residual graph for each edge E with capacity CE and current flow FE, right? So in this case, my capacity was initially, okay, let's take SA, right? S to A, my capacity was how much? Capacity was 1. And now my current flow, see, so in this example, conveniently, it was 1, right? If it was 2, and I just choose maybe let's say 1, right? My current flow is 1. So the residual or the residual graph or the reduced capacity will be my capacity minus the current flow. In this case, both are so 1 minus 1, which is equal to 0. And the reverse edge, yes, whatever is the current flow, that you add as the reverse edge. Yeah, so what you are saying that SA is equal to AS. That need not be the case always because let's say my capacity was 100 and my current flow is 1. So then this will become 100 minus 1, which is 99. And my residual edge will be, or the reverse edge will be FE, which is 1. Is that clear? Yes, it depends on the flow. Exactly. Okay. So this graph is the same thing what we constructed before, right? Let me see. Right, this is the same thing. So whenever I add a path, I add these residual edges also, right? That is this. or the reverse edge. All right, I add that. Okay, is this clear? Now, again, what do? I see if there is a path from S to T. I see if there is a path from S to T, right? So is there a path from S to T? So see, now if you see S to A has a flow of 0, right? So you can't push anything from S to A. So which other path is there? Can you tell me? From S to T in this graph? Snail is saying there is no other path. Does everyone agree? Including the yellow and the green edges. Okay, is there a path from S to T? Okay, so I definitely can't take this. S to A I cannot take because it is 0. Okay, what about this? S to B. I take S to B. Okay, now I can't take B to T because this is 0. But I can take B to A and then A to T. Is that a valid path? Okay, Nagarajan is saying SBAT. SBAT. S to B, this path, right? Yes, is that possible? Okay. Okay. So we take that path. All right. And we follow the same procedure. So this now becomes 0. Okay. And we add a reverse edge like this, 1, right? And this is yeah. So this now the flow comes from here, right? So this now becomes 0, and we reverse that by increasing this to 1. Then this, there's a flow of 1 here. We add a reverse edge, 1. All right. Now, is there any path from S to T? Is there any path from S to T? No, right? Because if I try this, this is blocked. This is also blocked. So here my algorithm terminates. And what is the maximum flow? The maximum flow is nothing but either what goes out from, sorry, there nothing can go from S to A, or like whatever comes, whatever is the sum of the reverse edges, right? Which is 1 plus 1 here, which is 2, or this, right? What goes from T to A and T to B. Those are the reverse edges, right? That is the maximum. So in a way, what is this saying? I actually added an edge. So this is, remember, these are reverse edges. So what that what that says is I have added, okay, I'll change this to my original path. What it's saying is that since these two are reverse edges, it means that in my original graph, right, I have two forward edges of length 1. And since these two are again reverse edges, I have forward edges of length 1, right, in my uh, flow. Okay, Snehal, is that clear? Maybe we'll also check the next example, so it will be much more clearer then. I think we have one more example. Okay, let me just take this. Yeah, again, right? Here, if okay, so here, how do we start? We choose any path from S to T. Hmm? Uh, so one path can be this one, right? Which is this, right? So although this is 30, we can only push 20 because this is 20 and this is 20, right? So we do that. We push 20. So remember when we push 20, what will happen? Let's say we push 20 here. For that edge, so this is 20 minus 20, which is 0. And we add 20 here, right? And this, we are pushing 20 here. So actually, this will become, how much will this become? 10? Is this 10 or will the, correct. Right, let me just check once more. Right. So we see that residual path will be 20, correct. Yeah. So what is pending? So what is pending is we can still push 10 here and we have to undo how much we have pushed previously. So that's why this becomes 20, right? Now again, we see if there is a path from S to T, right? So we obviously cannot take this. So this is the only option. So we take S, B, A, T, correct? S, B, A, T. So this becomes 10 minus 10, 0. We add the residual graph, residual edge 10. And now we are pushing 10 here. So this becomes 30, right? And since we are pushing 10 this way, we have to push 10 this way. So this becomes 20. Is this clear? And then we are pushing 10 here. So this becomes 0 and this becomes 10. Shouldn't be A, B, A. Sorry. Yeah. I made a mistake there. It should be 10. Sorry. Yeah, because we are subtracting. Yes. I'm sorry. And this will become 20. It's clear, right? Sorry. I made that mistake. Okay. And after this, we realize that there's no path from S to T because both of this becomes 0 and the maximum flow is, right, 20 plus 10, which is 30, or 10 plus 20, whatever, which is 30. Okay, I hope this is clear. Any doubt? So we are taking path SBAT, which is not in the original graph. SB. No, no. How are we taking SBAT? We are not taking SBAT, right? Okay, in the second, this thing you're saying, right? Yeah, yeah, yeah. In this iteration, right? Yeah, which is not in the original graph. Yes, which is not there in the original graph, but which is there in the residual graph, right? Yeah. So in a way, the residual graph is not telling us the path. It is only telling us how much flow, what is the maximum flow, right? So in that way, what it is saying is, hey, here you push 20 or you push something, but if you want to undo it, you can always undo it by pushing 10 in the opposite direction. So that is the function of the residual graph. It is not telling that there is actually a path from, so like there is a path SBAT, right? All it's saying is that you can calculate the flow using the residual. All right. I hope it's clear. Let's move on then. Shall we move on to the mock programming questions? So basically the value of the residual edge after all iterations tell us how much the capacity that edge in the graph has. Yes, you can think of it in that way. Yeah. So here if you see, uh, what it is telling is that you can push 20 this way, you can push 10 this way, right? And what about here? See, this is saying you can push 10 from A to T, right? And this is saying you can push 10, but you have to take back 10. So in a way, what it's saying is you can push. So this is 20 minus 10, which is 10 here, right? And you can push 20 here. So 10 and 20 go like this. 10 goes here, 10 goes here. Yeah, so maybe I'll redraw it. It's getting confusing. So S, A, B, T, right? So what this is saying is that you can push 20 here, right? And this is saying the residual graph has 10. So actually you can push 10 here. What is this saying? This is you can push 20, right? But you are getting 10 back. So which is as good as saying you can push 10 from A to B, right? The residual graph is like from T to B is 20. So you can push 20 this way. Here the residual graph T is from, yeah, there is an edge from T to A, which means that you can push 10 from A to B. Right. In that way, you can reconstruct the flow. So how do we determine the maximum flow? Either you take the flow here, which is going from S to, which is going out of S, or you take the flow which is entering T. So in this case, it's 20 plus 10 or 10 plus 20, which is 30. That is the maximum. All right. Yes, Snehal, hope it's clear. Yes, yes, sure. Yeah, you can try some more questions. You'll get a hang of it. Yeah. Okay, then I would say let's move on to the programming questions. Have some of you, okay, Nagarajan is asking how is total flow 30? Yeah, so 30 because, uh, so what is the question? I want to see the maximum I can push from S to T, right? So once we construct this final graph, right? Once we do this, what we have to just see is just look at how much can flow from S or how much can reach T. So if you see the original graph is this, okay? This is the original graph. So just by looking at this, you can see that the max, you can push 20 and you can push 10 here, right? Or you can receive 10 here and 20 here. That's the maximum, right? And from the Ford-Fulkerson algorithm, we realize that yes, indeed we can push 20 and we can push 10 here, or we can receive 10 and push 20 here, right? That's possible. So that's why the maximum flow is actually the amount which S can push or which T can receive. So in this case, it is 20 plus 10. So S can push 20 units from S to A and 10 units from S to B, which is 20 plus 10, which is 30. Or T can receive 10 units and 20 units. So it's 30. Okay, I hope it's clear. All right. Okay, so let's go to the programming questions. Okay, Nagarajan is saying only if you take A, B into account. Yes, yes. So if you don't have A, B, you cannot. So 20 units are coming here. You need to, and this has a maximum capacity of only 10. So yeah, so the 10 should flow here and 10 should come here. Yes. Is that your question? Hey, you can unmute and speak also, so I will get a better idea. Yeah. Okay. Okay. So others, have you all, yeah, did you get a chance to look at the mock questions? Uh, any particular one do you want, which you want to discuss first? Okay. Okay, just give me a minute. Nagarajan is saying did not understand PPA1. PPA1, you mean this? Acha, mock PPA1, right? Okay, let's see mock PPA1. Just pasted it here. Okay. So everyone, just let's try solving PPA1, right? Okay, I want you all to read the question, right? Maybe I'll just give all of you just 2 minutes to read the question, the sample input output. Is my screen, I mean, is the font okay? Should I just maximize it a little more? Is this fine? Okay, so what I'll do now is I'll give all of you 2 minutes, right? I see 68 participants now. I'll give you all 2 minutes. Read through the question, right? Tell me some strategies, right? Don't directly start writing the code, but think of some strategies which will work. Okay, so I'll give you 2 to 3 minutes to think about it, and we'll continue. Sure, Nagarajan, I'll explain the problem statement. I just want others also to just read, then we'll come back to it. Okay, everyone. I hope you all could understand the question, right? Let's go through the question once. Let's try to understand the question, right? So what it's saying, you're given two lists, A and B, right? Both have the same number of n positive integers, right? And you can apply the a swap operation, but any number of times, right? Which and what is peculiar about this swap operation is that so let's say this is A. So if this is A and this is B, when you swap, let's say when you do the swap operation, you can swap element and the ith element of A and the ith element of B. You can just swap both of them, right? AI becomes BI and vice versa. Okay, I hope this much is clear, right? Now, what you want to do is you want to minimize the maximum. Okay, that's why it's called min max. You want to minimize the maximum, the product of the maximum of the two lists. Okay, so it's a mouthful to say that, but what does it mean? You have a list A, you have a list B. So what is the maximum? Okay, let's say we don't do any swap operation, right? What is the max of A in this case? Can you reply on the chat? Without any swap operations, what is the max of A? 6, right? Max of A is 6. What is the max of B? 5, right? So 6 into 5 is 30, right? But obviously, this is not the maximum. Sorry, this is not the minimum value which we can get, right? If we were to perform the swap operations, like let's say we were just so let's say we were able to swap 2 and 4, right? And this 2 and this 5, right? So now my array becomes 1, 4, 6, 5, 1, and instead of 2, it will be 5, right? It will be this. And we know the max of this is 6 into the max of, now my B is actually 3, and instead of 4, it will be 2. So 3, 2, 3, 2, 2, and instead of 5, it will be 2. So max of this is what? 3, which is 18. And that is the minimum possible value of the product of the maximums. Okay, it is the minimum possible value of the product of the maximums. Okay, Nagarajan, now are you able to understand? So the question is saying you apply how many ever swap operations you want, but I want this maximum, the product of the maximums to be the minimum. Okay, I hope this is clear now. I want the product of the maximums to be the minimum. Okay, so how will you go about doing this? The example itself gives us some hints, right? Like what should be done. So if you go through the example, you will get some idea. Okay, why have they chosen, in this example, why have they said, why have they swapped only 1 and only 5? Why not anything else? Right? And why have they done that? Are they following some strategy? Yeah, if you all have some ideas, you can reply in the chat. You can message in the chat.
Yeah, so I think one strategy can be to compare or find the max of both the arrays, and the least of them you can bring over to the other side.
Find the max of both arrays. Okay.
And the lesser of that you can bring over to the array which has the max element. So that way what you're doing is you can reducing the max of the other array. So there is a potential of reducing the product of max of both arrays.
All right. So you're saying find the max of both the arrays and whichever is the
Swap. And then swap the least of them.
okay.
Okay, so maybe this will sound confusing. Okay, so you're writing
Okay,
down, that's a
let's
good
take
thing. Yeah.
yeah, yeah.
So first step is we find the max of both arrays, right?
Right, right.
And I think
So
the second step should be to find also the min of both arrays.
okay, fine, fine. Okay. All right.
And the third step,
Hmm.
so yeah,
Okay. Yeah, yeah. Go ahead. Go ahead.
yeah. Third step is to swap the min of the first step. Yeah, find min.
Hmm.
Okay. The third step would be to swap the min of the first step and the max of the second step. That may not be enough. Maybe I have to go into some sort of an iteration or a recursion, but I'm just thinking out aloud.
Sure, sure, sure. Yeah. Good try, Nagarajan. Yeah. So so you swap the min of step 1 and the max of step 2. Okay.
No, I'm not too sure. But will that swap the element of one array into the other array? I'm not sure. So maybe I'm not right there. Okay.
Yeah, yeah, yeah. So because uh, the the swap operation cannot, suppose the max was in, let's say, the second position. Sorry, the min of the max was in the second position. And if this was in the
Yeah.
third position, we can't swap it. It's not possible.
Sir, I have a strategy. Should I say it or no?
Yeah, yeah, yeah.
No,
Yeah, yeah.
because
Who is this? Who is
this,
this? Sorry, I can't see it. I mean, no, I can't see your name. Who is this?
yeah, it's Hanani.
Hanani. Yes, yes. Go
Yes.
ahead. Go ahead.
So,
Tell,
but
tell.
the problem is this actually works. So, what is, should I say it?
Okay. How do you know it works?
Because I tested it in the portal.
Okay, okay. Then maybe let's wait. Let's wait.
Yeah.
Okay. I'll come back to you. I'll come back to you. Okay.
So what works?
No, I'm just saying, Hanani is saying he tested it out in the portal and it is passing the test cases. So he was asking me, should I tell it right now? I said, we wait. Let's see if others can also come up with some solutions. Then we'll go back to
Okay,
it.
okay. Yeah.
Yeah. So just looking at it, uh, what can be the strategy which we should do, right? Any other ideas coming? Or if you just look at what this example tells, like why did they choose to swap one and like the indices 1 and 5? Why did they perform only there? Right? Does that give us a clue? Others, any other suggestions, any other strategies?
I mean, one thing is clear. You want to bring over 5 to the side of 6 so that 5 is no more the max on the other side, and 6, you can't do away with 6 because it will still be max for either of the arrays, right? So the one thing that you can do is reduce the max of the other array. So
Okay.
basically what you're doing is you're masking 6 over 5 on one array.
Okay.
And what we have done is the next max, which is 4, has also been swapped so that the second array has a max of 3, which will further reduce the product. Right? So there are tools. So, but if you go few steps further and try to swap 3 out of the second array so as to make 2 as the max, you won't have any more elements here in the first array. So when you want to swap 3, perhaps the only element you will have here, but you have 2 ones, which you could have still swapped. Don't you think so? See, what we did was we swapped 5 with the, what did we swap? 5 with 2, and then we swapped 4 with 2.
Swap,
I think
then
we
we
could have,
swap,
yeah.
right?
Don't you think we could have still swapped both the 3s with both the 1s on the other side?
This one is saying, 1 and 3.
Yeah, 1 and 3, 1 and 3 again. Oh no, it has to be the same index, right?
Yeah, it has to be the
It has to be
same.
same index. Okay. So when you do that, you possibly exhaust all the possibilities.
Okay.
Yeah.
Okay, I want to hear from others. Any other strategy? What do you think about this? What Nagarajan said about reducing the max of one array? No one else? No one else has anything to share? Anything on the chat? If you don't want to speak, you can reply on the chat also. Anything else? Okay, Hanani, go ahead. Yeah, let's see what strategy did you follow?
Yes, sir. So basically, first what I'll do is, so mine is a O of n solution.
Okay.
So first I will find the max of L1
Okay.
and simultaneously keep track of the index of the max of L1. Like where is the max situated in L1?
Okay.
Next, I will loop over L2.
Hmm.
Okay.
Okay.
And if the element in L2
Hmm.
is greater than the corresponding element in L1,
Element in L2 is greater than element in L1. Okay.
I will swap
Then you will swap. Okay.
and if you find the maximum of L2 and multiply it with the maximum of L1 we found in the first step, you'll
Hmm.
get the answer. But there is one caveat here,
Hmm.
and that caveat is if let's consider an array 1, 2, 3, 4 and 1, 2, 3, 5.
Okay. Let me just 1, 2, 3, 4.
And 1, 2, 3, 5.
Ah. So let's see what your strategy is. Your strategy you're saying is max
No,
of L1.
my current strategy fails in this case where the maximum is on the same index on both the arrays.
Hmm.
So that's why in third step, you just have to add one more if statement, and that is you only swap when the current element is not equals to the index we found in the second step. Okay, I think.
Hello?
Yes, sir. Yes, sir.
Yeah. Go ahead.
I've also sent the code in the chat.
Okay. Let's see. I'll just copy it. Can I get it? Okay. I'm able to get it here. So what you're doing is, okay. Yeah. So you are iterating through the list one, and if L1 I is greater than X. Okay, why have you put X as
We are just trying to find the maximum of L1 in the first 5, 6 lines.
okay. And that is getting stored in X.
Yes.
Okay. And
And
index,
is also being stored.
all right.
Yes. In the second for loop,
Hmm.
if the element in the B, L2 is greater than element in L1, I will replace the element in L2 with the element in L1.
Okay, this is a swap, right?
Yeah,
In a way.
this is the swap. But just I added that I is not equals to index condition.
So that it is you don't swap the maximum.
Yes.
Uh,
So if I follow without that I is not equals to index, the arrays which you wrote above 1, 2, 3, 4 and 1, 2, 3, 5, it would
hmm.
result in 16, but the answer is 20.
Hmm. 16 how? Like
But the answer is 20, right, sir?
the answer is 20.
Yes.
No. How is yours? You're swapping it, right? So this will become 5 and this will become 4.
Yes, but I already calculated the maximum of the L1. So
Oh, okay.
yes, yes.
Okay. So basically what you're doing is you are calculating the maximum at L1 and you are checking this condition here, right?
Yes.
So if L2 is greater than L1, you swap. And of course, you're checking the same index also, right?
Yes.
So in a way, what you're doing is that you are somehow trying to put all the maximum elements into L1 in a way. Is
Yes.
that your strategy? I think someone told that. I think you only said, or someone said this, no? Who said this? Reduce the max of one array.
Right.
I-
Yes.
Is that what you're trying to do?
Basically, that's it. Yes.
Others, any comments? Uh, what do you all think? No comments? Okay, everyone is very silent. Is this a very hard problem? I mean, uh, to understand at least, you all are getting like getting some idea, right, of what we should do. Okay, so yeah, I'm not giving the answer. I want you all to try it out. What if Faiz is asking what is y equal to 0? Yeah, Hanani, what is y equal to 0?
It is the variable for the maximum of L2.
Yeah. So it's just some initialization, right? Oops. Yeah, so I'm just wondering, Hanani, uh, why do you actually need all of this?
Because, sir, I would like to calculate where the maximum element is at. Or else I could have just said x is equals to max of L1.
Okay, so I'm saying, is that really needed? Without that, will this code work?
I don't think so, sir.
Suppose if I'm just checking this condition, if L2 is greater than L1, I do a swap. If L2 of I is greater than L1 of I, swap.
Okay, and then we will calculate the maximum of L1 and L2, which would give us the
And
answer.
multiply.
Yes,
Yeah.
yes. Okay.
Okay, Faiz is asking, is it like inversion? Uh, I would say it's not as difficult as inversion, right? It's a simple problem, right? So it is a greedy approach which you are following in a way, right? Oops, sorry. Right? You are checking each element. You are looking, and your goal is to somehow push all the maximums into one array so that, the product will, reduce, right? Because the other array will have, and thereby you will get the product which is minimum. So it is somewhat like a greedy strategy which you should follow. Okay, Nagarajan is asking, is this order n? Hanani, what do you think? Is it order n? Others, what do you think?
I think it is order answer.
Okay, why do you think so?
The first for loop is definitely order n. And yes, sir, do you agree or no?
Yes.
Yeah. And the second for loop is also order n.
Is max of does it have any order, sir?
I
See,
think it,
max also, yeah. So this max is outside the for, right?
yes.
Hanani?
Okay,
It's
fine,
outside
sir.
the for.
Well, sir, even if it is inside the fur, it is just only one operation, right?
See, but how do you ideally calculate max? Oh, sorry,
Through
max
iteration.
of, oh, it's just
Max
max
between
of
two numbers, not
two
any value.
numbers. Yeah,
Okay,
yeah.
okay, two
Sorry.
numbers. Oh, sorry.
Yes.
Yeah, yeah. Even I thought it was max of that. Yeah, yeah. Two numbers, it's a single operation. Correct, correct. Yeah. All right, good. I'm not giving the final answers. I'm just directing you all towards possible solutions. Okay, good, good. Okay, let's move on to PPA 2. Okay, I want you all to think about this problem, right? I'll give you 2-3 minutes to read through the problem, and let's think of strategies which we can use. Okay, let's join in. Okay, everyone. I hope. Yeah. So this question is. I hope this question is clear, right? Yeah. So the question I hope is simple to understand. It's like you have a list which has a certain property, right? Which is unimodal. Unimodal meaning it, if you see, it increases up to a particular point. I mean, the elements keep on increasing up to a particular point. Okay, it reaches a reduces, right? And what the function should do is to return the position of the peak in A. So in this case, it's 0, 1, 2, 3, 4, 5. 52 is the peak. And after that, you see everything is reducing. So 0, 1, 2, 3, 4, 5, it should return 5. Here 8, 9, 3, 9 is the peak, it should return 1. Of course, if you wanted an order n algorithm, what is the can you tell me what is the order and algorithm for this? Anyone, what is the order and algorithm for this?
So build a min heap, and where we have to do the heapification, that's where we stop.
Okay. Even simpler thing.
Okay, let's go through the array.
Yeah. Just a max of the list will give it, right? Yes, correct. Max. So of course, that's not what the question is asking. The question you want to do it in log n time. So log n, like once you hear log n only, some things just come up, right, in your mind. Binary search, and he's saying, Joyce is saying something like binary search, compare the middle element with left and right element. Okay, Joyce, can you elaborate? What do you mean by
So it's like we take the middlemost element and compare it with the previous element and the next element. And so this is just a very vague idea in my mind. Like
okay?
then if it is like say in this first thing, I think 51 is a middle element. So you see that if based on that thing, whether it's increasing or decreasing, like that, you move either the pointer, like the middle element, to the like the thing to the left hand side or the right hand side and take, and then again compare it, something like that. There
Okay,
was,
okay,
I think there was one practice assignment problem, something like this. Some practice PPA, like somewhat similar to that. And you keep
okay,
on checking, and then when you find the maximum element, then put on the other two elements. I mean, you can note down the position simultaneously with the thing and do it.
okay, okay. Okay, so I think what you're saying is first you take the middle element, right? And then compare it with, like you were saying something, compare it. Suppose the middle element is, let's say, M, okay, some M,
Yeah,
or the M, sorry, mth index. Okay, this is the
yeah.
index. Okay,
Then you compare it with m minus 1 and m plus 1.
so compare AM with AM
Plus 1 and minus 1.
Okay, why are you doing this? Why do we want to do this?
So we can know on which side is the maximum element. If say in this case, for 51 is the middle element, so you compare it with the next element and you find it is decreasing, then you should be sure that the maximum element is on the left side, like the lower portion, like below 6, somewhere below 6 or 6 or below 6, something like that.
Okay, okay. So
I mean,
then what do you do? Yeah.
then you take up the lowermost portion, like till 6 you take it, and then again take that portion and do some similar, like a recursive function, and find out which is the maximum element.
All
Like
right. Yeah.
here again, it will become 3. Like 3 would be the middle element in this list. So you know that the maximum lies somewhere on the right of 3. So you take 4, 5, 6, that list, and then you again compare and find 5. So you come to the middlemost index, like the maximum index, not index, like the maximum element.
Right. Okay, good attempt, Joyce. Good attempt. So, good. So, what made you think of this solution? Yeah,
Yeah,
like
log n is a thing that somewhere something related to binary search or dividing the array into 2 and going about it. That what.
right. Okay, very good. So, you gave a good summary, right? So, the thing with login is whenever you think of login, definitely binary search comes to our mind, and at each step, you want to somehow eliminate half of the list, right? And yeah, I think that's what you have tried doing here. Others, what do you think about this strategy? Will it work? Any other ways to do it?
Yeah, that should work. And the other strategy could be to do median of medians and then do a kth element to find the largest,
Median of median and
find the largest element, kth element, because we are trying to find the largest unimodal.
But
okay.
can't we use the inbuilt functions?
Sorry, I could hear someone.
Yes, sir. I told that can't we use the inbuilt functions that we will take the max of the list and return the index of that, because the inbuilt functions do, they work based upon the conditions now.
So if this is the list, just take max of the list.
Yes,
That will give you the answer.
here 51, and then return index of L, index of max L.
Right. So yes, definitely that will give us the answer. But remember,
And that
how
is
much
not
time?
taking, it
Yeah.
is running just for the first test case and not for the other two. But my point being, it shall take no less time, because the inbuilt functions are designed in a way that it will take less time.
Yes, but like in terms of complexity, right? How much time do you think max of L? You might have used max the inbuilt
Yes,
function
sir.
max, right?
Yes, yes.
Yeah. So how much time do you think it takes?
Probably 1.
No, I meant in order of n, right? Let's say there are,
O1, O1,
sorry,
O1, probably.
order one. Okay. Okay, what do others think? Can it be done in
It may
order
be
one?
ON. It may be ON, I'm not sure of.
Oh, if it's order,
Of N, then it's, it is problematic, but it shall take O1 only. Let me see.
what about others? What do you think? So yeah, so one thing is, yeah, we really don't know uh, how they have implemented Max, right? They might have used binary tree or whatever that we don't know. But generally, what the most simplest strategy is you iterate through the list, right? And then you see which is the maximum, you store it in a value, and you go ahead and see if the current element is greater than that, then that becomes the maximum. So you have to do one search, right? One through the entire list, right? And so it should generally take order n. Okay. So you are saying the test cases, some test cases are not passing, right, Anushka?
Yes, sir.
Yeah. Why do you think that's not happening?
Probably
Why do you
this may
think?
be the reason ON1. So we can go for binary search, but again, it could take more lines of code.
Right. Right. So remember, we are checking for the time complexity, right? Not the space complexity. So we are really not concerned how many lines of code uh, uh, the program is, right? Because big concern for us, right? And how much difference? Like this is the one line. The login algorithm might take how many? 20, 30, 40, 100 lines, even if it takes, right? The difference is not substantial, right? But if
Yes,
you,
sir.
if you, yeah, and you all know this, right? Order n and order log n.
It's big difference.
Yeah. So if you take 10 to the power 10, sorry, 2 to the power 10, and yeah, so if you have 2 to the power 10 elements, this will take 2 to the power 10 seconds. This will just take how many seconds?
It would take 3.93.
Yeah, 10 seconds, right? Yeah, yeah, that's fine. So see, you see, there's a huge difference right here. But space-wise, irrespective of the number of elements in the list, the space in both the space complexity or the difference in space is going to be constant, like the size of the program, right? Okay, so that's why the strategy which Joyce said, okay, that is definitely a log n strategy, right? At each step, we try to divide or try to split this list into two parts. Somehow, one part, keep that part, keep on doing that until we get the maximum, right? Okay, that's all I'll say for this. Uh, the strategy is simple. I think you all will get it. Okay, I want you all to try it out. Maybe one more uh, drawing which might be helpful for you is this. Okay, so let's say this is my I and this is my A of I. A of I. So what is actually, so this is like a graph. So what is happening as I is increasing, A of I is increasing somewhere, and then at a particular peak, right? This is the maximum, and then it decreases some, right? Okay. Now, of course, right, that strategy of taking the middle element, right? We try doing that, and you will realize that there are three possibilities for where this middle element M can lie. Okay, mid. Okay, what are the three possibilities? Can you reply on the chat? What are the three possibilities for where the middle element can lie with respect to this graph? Okay, Ashwin is saying rising slope. For rising slope, it can lie somewhere over here. It can lie on the falling slope somewhere over here, or if we are lucky, it will be on the peak. Yeah. So Vivek and Hemant all are saying the same thing, right? So let's say this it's somewhere over here. Somewhere over here. This is case 1. It's somewhere over here. This is case 2. And this is, let's say, case 3. Right. Okay. So let's say it's somewhere over here. Let's say M is here. So how do we know M is here? How can we be sure that M is on the rising slope? Okay, Ashwin is saying A of M is less than A of M plus 1. So you're saying case 1, A of M is less than A of M. Hello, can you hear me? I think my mic is off. Can you hear me now? Someone on the chat, can you reply? Yes, no, okay, good. All right. So A of M is less than A of M plus 1. Will this work? What if my M was here, just one before the middle element, the maximum element? Suppose if my M was here and M plus 1 is actually the peak.
I think we should do comparison between 3 numbers, not just 2.
Sorry?
We have to compare 3 numbers, like in a series, like M minus 1, M minus plus.
Very good. So you have to check we actually have, if it will be in the rising slope, to be sure that it's on the rising slope, we actually have to check, we have to do 2 comparisons, or we should check 3 numbers, right? A of M minus 1 and A of M plus 1, right? If this is true, then we can be sure that it is here. Okay, is this clear? And if this is the case, what should we do? If this is the case, what we should do? What should we do? What do you think? What should we do?
So we can move start to the middle.
We can move the start. So you're saying start is, let's say initially it was here. So we move it here.
Yeah. So in this way, we can neglect all the left part.
Right. We'll neglect all of this and we take, so we are taking start is equal. So you're saying start is equal to M, right?
Yeah, M.
And the end will remain the same, right?
Yeah, yes.
All right. Okay, good. So that is a strategy which you all have to follow. Okay. The same thing, if it's lying somewhere here, you have to check for some other condition, change, yeah. So I won't discuss that, but yeah. So I just wanted to give you all an idea. Finally, Okay, can you tell me when will case 3 happen? What is the condition we need to check? Case 3 is the actual, we
Yeah.
get peak. Can you all tell me what that is?
So when the left and the right are both less than the middle.
When the left, so which is a of m minus 1,
Minus
let's
one.
say.
Yes, m minus 1 is less than
Okay.
middle am,
Okay.
and am is also greater than am plus 1. Yeah, am plus 1.
Great. So, okay, so I hope this is clear, right? Then we get the, we return m and that becomes our peak. All right. Yeah, I want you all to try this out. Okay, it's not very difficult. Okay, let's move on. Yeah, let's move on to a graph problem. PPA 3. Yeah. Okay, so this is PPA 3. You will see that in the portal, along with along with some prefix and suffix, you have the Dijkstra's algorithm also with you. Okay, that's already provided to you. So you have to use the Dijkstra's algorithm. Yeah, but I want you all to just read through this and think of some strategy which you can use. Right, or just or you can look at the portal also to see the entire thing. There's an example also given. Yeah, so I'll give you 3-4 minutes to think about this. Yeah.
Okay, everyone. I hope you all got a chance to look at the problem, right? Maybe I'll just explain in brief what the problem is, right? So you're given a graph like this, right? And you are given the input is you are given the number of nodes, okay, and you are given the edges, right? 2 zeros tells me that there is an edge, it's undirected. You have an edge from 2 to 0 of weight 11, right, and so on. And you want to start from a source or from a start city, let's say, which is 0, and you want to come back to it, right? You want to come back to it, and that should be the minimum. That should take the minimum distance, right? So of course, if you go from 0 to 5, you cannot come back from 5 to 0. That's not what it says. There should be some intermediate nodes in between, right? So for example, this can be one path, right? 0, 2, 3, 5, 0, or 0, 2, 3, 4, 1, 5, 0. Yeah, actually these are the only two paths, I guess. Correct me if I'm wrong. Yeah. Right. So you want to add the output should be the length of the minimum cycle, right? In a way. And if you look at the code, I mean the code which is given in the portal, Dijkstra's algorithm is already given to you, right? Yeah. So any thoughts on how you would go about doing this? Anyone? Yeah, let's look at the graph itself. Yeah. Can we use Floyd-Warshall? Vivek is asking. Floyd-Warshall is all pair shortest path, right? Yeah, how will you use it? Yeah, I think you can. We need not find the question is not saying from all nodes, what is the shortest path. It's saying, it is telling us that, the source, the start city is given, right? I just need to find out cycles from that city. All right. Any other strategy? Anything coming into mind? Okay, Priyanka is also saying Floyd-Warshall. Yeah, so how do you think? Okay, let's say we use Floyd-Warshall. How will we, what is the strategy you will use? Floyd Warshall, what is the strategy? Okay, Priyanka is saying along with the path, store the parent details and retrain the steps. Okay, so you'll get paths, right? Is that what you're trying to say? Okay. But then again, we'll get paths from all vertices to all other vertices. And from that, you can choose the source and then you can check it. Yeah, but you're doing more than what is required, right? I don't want paths from all vertices to all other vertices, right? I just want from the source back to itself, right? Okay. So even in the prefix code, Dijkstra's, you have to use Dijkstra's algorithm. And the code for Dijkstra's is already given. Okay. So let's think about it. No. So let's say which will give me. Yes, Priyanka. Yes, we have to use Dijkstra's. So from the source, so what does Dijkstra's do? It gives us from a source S the minimum distance, right? So Priyanka is saying we can find the closest nodes to the source and find those paths.
Actually, Dijkstra's algorithm will give you the shortest
All right.
distance to all the nodes, right? So we can call Dijkstra's function twice to get the distance from source to an intermediate node, and then from that intermediate node back to the source again, and then add those two paths.
Okay, can you repeat, Nagarajan? Yeah. So
what
you
I was saying is,
yeah, go ahead.
Yeah, so what I was saying is, we can call Dijkstra's algo function twice to get the distance between source and an intermediate node.
Okay, so what will this?
You're actually breaking up.
Yeah, I'm sorry. Can you hear me now?
Yeah, I can hear you now. Sir, we can't hear you.
Sorry about that.
We can't hear you.
Hello, can you hear me?
Yeah.
Okay, sorry. Share again. Okay. Yeah, the admin has to make me host. That's okay. Yeah, Naga.
Yeah.
Yeah, tell me.
Yeah, what I was saying is Dijkstra's algorithm gives you the shortest path from a source to every other node, right?
Yes.
So if I can make 2 calls to Dijkstra's algorithm, first to get the distance from the source to every other node, and then some intermediate node to every other node, which will also include the source node. Then I can add up those two, source to an intermediate node, and then an intermediate node back to the source. Now, how would I achieve that? I have to write and find out. But the strategy is that.
Right. Okay, that seems like a reasonable strategy. What do others think?
Sir, in Kruskal, we have a component that we use to avoid going into circular paths.
Right.
If somehow we can modify it to not avoid but to go into circular paths and use Dijkstra's to choose minimum nodes or the minimum distance. But problem is I don't know how to use this, how to align that with Dijkstra's.
Right. Yeah, I'm getting what you're saying. Just give me a minute. I'm not able to share my screen. Just give me a minute. All right, yeah. Hopefully it should start share. I should be able to share. Right. Okay, I'm not able to share. Just give me a moment. Okay. All right. Yeah. Hope you can see my screen. Okay. Yeah. So what Nagarajan was saying, yeah, you calculate Dijkstra from S to some intermediate node and then apply Dijkstra's from Nagarajan. Hello, can you hear me?
Yeah, we can hear you. Yeah.
Yeah, yeah.
So
Yeah, go
basically,
ahead.
since this is a circular path,
Hmm.
I mean, I need two minimum distances from source to some intermediate path, and then from an intermediate path back to the source, because the one call to Dijkstra will only give me the minimum distance from a source to every other node, which will not include back to its own place.
Right.
So I have to devise a strategy to send two calls to Dijkstra's algo so that I can get two distances and then I add them up. So, I mean, this was, I think, one of the graded assignment questions back then. I've forgotten how I did that back then using this strategy only, but I'm not able to recall it right now.
Okay. Good attempt. Yeah. Okay, so let's see what that means. Okay, let's try doing that. No, so I call Dijkstra and I take S. In this case, let's take that as 0. So Dijkstra returns us a distance kind of a data structure, a dictionary, which has its distance from 0 to every other node, right? So 0. The distance from 0 to 1 is, in this case, yeah, it will be something. Okay, something from 0 to 2 we know is, looking at it only, we know it's 11. From 0 to 3 we can say it's maybe 21. 0 to 4 is something. 0 to 5 we know is 12. 0 to, yeah, that's it, right? Okay, so now let's say we've got this, we have made the first call. Yeah, so now I think the question is, what is this intermediate? So once we know that intermediate, so Dijkstra some, let's call it some I. So then we have to just call I and we'll get some distance. And what we have to look for is the S entry, right? Which tells me that is the minimum distance from I to S. And this is telling me the distance from S to I. I have to just add it up. Right. Okay, I think that's you're going on the right track. That's how you should do it. I won't tell the final thing because I want you all to try it out. Yeah, but that is the general strategy which you have to follow, right? And Ashwin also has given something, right? You can. So what he's saying is we can take any one of the neighboring vertex of S, then remove that edge and apply Dijkstra's from S to that vertex. Minimum of all such would be the answer. Okay. Okay, so I want you all to try it out. Okay, so Ashwin and Nagarajan, both of you are on the right track. Yeah, it's a combination of something of that sort. You will get it. Okay, now we don't have time, but I'll just quickly just take you through the last PPA. Okay, this is an interesting one. Okay, again, I'll give you some 2 to 3 minutes to read it. Yeah, more details are there in the portal. like, but for now, I think we can try this.
So for the home proctored exam, will we get similar questions like these or of same difficulty?
Roughly the same difficulty. Yeah.
So we won't be asked to write any algorithms, right? For example, for Dijkstra, as you said in this particular question, Dijkstra's algo has been given, and then we use that to solve a problem, right?
Yeah.
So mostly it will be like that, isn't it?
Yes. Yeah.
Okay.
Yeah. At least for the graph, because the graph algorithms, yeah, they are very tedious and all of that.
Yeah. Okay.
Okay, you all can read through this problem, right? And think about this. I'll give you a few minutes to go through it. Okay, so yeah, so this is a difficult, or yeah, it's been asked in the National Olympiad, so it's not a very easy problem, right? But yeah, so what are your thoughts on it? Are you getting an idea of what type of problem this is?
So like, I think it's a dynamic problem, dynamic programming question.
It's a dynamic. Okay, why do you think so?
So because we can like split this into sub problems, right? If the first tile is placed vertically, then I can easily find out the difference in that case, and I just have to find the problem for another rectangular tile of length 1 less than the original. And if one of the tiles were placed horizontally, then I have no choice but to place a second tile, the one below it also horizontally. Then it would be like solving a domino problem of length 2 less than what was the original. So again, I can split it into sub problems of similar type. So I think it should be done.
Good, Ashwin. Yes. So you're right? So this is a dynamic programming problem, and as Ashwin said, so if you consider this entire thing, you can divide it into sub problems, right? So if you're starting from here, there are either you can. Okay, so before that, have you all understood the problem? Any doubts in the problem? Do you want me to explain the problem once?
So the only thing, the doubt that I have is that whether it is compulsory that once you have one vertical tile, the adjacent one will be horizontal, or can
No.
that also be? So that's not compulsory.
That's not compulsory, right? So you can have something like 8, 9, 6, 7, 2, 1, 3, 2, whatever. No, there's no rule like that, right? Yeah. So So the question is, yeah, you have tiles like this, and it can be, there will only be 2 rows, but the number of columns can vary, right? It can go on, and your task is to either, choose elements in this way, vertical, or it can be horizontal like this, right? You have to choose. You have to choose them in such orders, such that and what they say is, the no pair of tiles should overlap, and the score for each tile is the difference between the smaller and the bigger, right? So this is 9 minus. So if we consider this case, which is this, the 9 minus 8 is 1, 6 minus 2 is 4, 7 minus 1 is 8, 3 minus 2 is 1. So the score for this is 1 plus 4, 5, plus 1, 6 plus 8, 14. Whereas the score for this is, can you tell me what is the score for tiling 2? Okay, I made a mistake, I think. What is the mistake? 7 minus 1, 6.
8, no? 8, sir?
How is 8? 8 minus 6 is 2.
2.
9 minus.
Yeah, this is also, and these 2 are 1.
Right? 2 plus 2,
6,
4,
6,
5,
6, yeah.
Correct. Right? And our objective is to maximize the score, right? So what should, so and our task is to compute the maximum score, right? Which can be, which we can get.
Sir, in this question, we can use some sort of greedy approach to look for those tiles whose difference is maximum, like the 7-1 or 6-2. And then we can align, we can choose another tile which has the maximum difference. And in that way, after a while, that we can choose any tile which align with them.
Okay. So so you look at a tile and you look at its adjacent
tile, yeah.
Okay.
That and we will choose those tiles who has a maximum difference, like 7-1, or we have, if the one with 9, so we can choose 9-1. And then
we can't choose 9 and 1.
No, I am saying if the one would be there.
Right.
And then we after leaving that, we can choose, we can go ahead and choose 2 adjacent tiles which has next maximum.
Okay.
And I think in the end, there could be a problem.
Yeah. What do you think the problem is? Yeah, good. That's a good attempt. No, see, this is how you should, you should also think, why will the greedy approach not work? Others, what do you think? Will the greedy approach work?
Okay, so that the problem might be, suppose we choose 9-7. Suppose we choose 9-7, and then we choose 6-2. Then we cannot actually the 2 below 2 there is 1, and the 8 is remaining, and there is no way we can create a tile with them.
No, even if you we'll take only contiguous elements. No, in this case, we'll either choose 8-9, 8-6, or 9-7. Okay.
8, 9, 8, 6 or 9, 7. Yeah.
Okay, so here itself we are seeing that the greedy approach won't work. So 8, 9 is the score is 1, right?
Yeah.
8, 6 and 9, 7, the score is 2.
2.
So according to the greedy approach, let's go ahead with these two, right? We should, according to the greedy approach, this is better, right?
Yeah.
Because you're getting score of 2 and 2 plus 2, 4. Whereas if we took 8, 9 and 6, 7, the score is only 1 plus 1, 2.
1. Yeah. The maximum score is 1 only.
Yeah. But then we see it's not working out, no? Because and this will give us a score only of 6. But if we had taken 8, 9, although it is a minimum, later on we can choose things which are greater and then we would get a maximum score.
Sir, can we adopt some type of strategy like, there was one, I'm forgetting where it was covered, like sort of, when you're trying to find which is the minimum distance between 2 points, in which you were checking that it's only possible to have in the next 15 grids. So you only have to check 4 grids. So maybe could we do that, that you can have a fixed configuration. You will not have so many configurations. With fixed configuration, you just check for the neighbors. Like for example, you check 8, 6, 9, 7, but you also check what happens in the adjacent ones. And wherever you find sort of maximum, that you can choose.
Okay. Yeah, but in this, let's say we make some local decision, let's say up to here or something, right? But it can very well be the case that later on there might be other elements and maybe the choice which we made here was wrong, or we might have to choose something there and that would result in changing all of this. Is that possible? That's also possible, right?
Yes, that is possible. So probably it's like finding all various paths and then like very time consuming probably.
Right. Right. So what Ashwin said and what you're also getting at is, Nagarajan, you want to say something?
Yeah, I mean, can we use brute force? I mean, since it's not given that you should achieve this in log n time.
Yes. Yeah, why not? So what will the strategy be?
I mean, try to find the difference between, I mean, so this data is available in 2 different arrays, is it? I've not read through the question, but how the data?
Yeah. There are 2 different arrays. Yeah, this one and this one. Yeah. So this is, I think, take it as a list. Yeah, this is L and this is M, for example.
Yeah. So between 2 different indexes, same indexes.
Yes.
Or between adjacent indexes, if I can get the distance and take the max of that to pair up the elements, then that could give me a strategy. I mean, that's brute force, of course. I mean, since I will have to compare, but I won't have to compare everything with everything. I'll have to just compare 2 different 2 neighbors, adjacent neighbors. Not any more than that, right?
Right. Right.
So elements in the same index across the array or within an array, adjacent elements. If I compare instances and I pair up those that have a maximum distance or the difference, and then use that distance to then add up, will give me the maximum score.
Right. So is it like similar to the greedy approach? Like you're saying you will you will check 8, 9, you will see that the score is
It's
1.
not greedy actually.
Okay.
Yeah.
So how will you make a
Yeah.
decision?
So I'll do 8, 9, 6. So I'll do 8, 9, 6, 7, 2, 1, 3, 2. I'll also do 8, 6, 6, 2, 2, 3, 9, 7, 7, 1, and 1, 2.
Okay.
And then sort them because they are possible pairs, right?
Okay, so you will
And then
find
take the
all
difference and
possible
add them up.
pairs. All pairs, possible pairs.
No, actually, I'll pair all of them up, and then I can actually sort them based on the difference, so that the highest is at top. And then I just take the difference and then add them up, running total. So for example, I have the difference of, yeah.
Yeah. So let's try that here. So let's say, so you will do 8, 9, let's say 6, 7, 2, 1, 3, 2.
Yeah. So same indexes.
So the okay. Let me write it here. 8, 9, 1, then 6, 7, 1, then 2, 1, 1, 3, 2, 1. All right, we got that.
And then 8, 6.
8, 6.
Then 6, 2, and 2, 3.
6, 2. Okay. 8, 6 is 2. 6, 2 is 4. And 2, 3 is 1.
Yeah.
Okay.
And then 9, 7, 7, 1, and 1, 2. Yeah.
9, 7, 7, 1, 1, 2. 9, 7 is 2. 7, 1 is 6. And 1, 2 is 1. Okay. All right. Now you will sort it. Okay, I think what Ashwin is also saying, if you find the pair of maximum difference first, Nagarajanya, do you is what you and Ashwin saying the same thing? Yeah, you can look at his comment.
Yeah. Greedy approach.
Okay, you can tell me your strategy. Yeah. So now from this you will choose 7, 1, right?
I'll use 7, 1.
I will. Okay.
And then I'll choose 6, 2.
Then I will choose 6, 2. Okay.
Yeah.
Then.
Okay. Then obviously, since I've chosen 7, 1,
yeah,
I cannot choose any other pair that is 7.
Right.
And I cannot choose any other pair that is either 1, 2, or 6. Right.
Yeah. So then you, yeah, it's like something
then
like
whatever is left.
Yeah.
Is what.
It looks correct. I'm just thinking, can we get some counter exam? So the greedy approach, that's the thing, no? If you get one counter example, then you know that it's not right. Right. So
yeah,
for now it looks correct, right?
Yeah, so that will actually leave only 8, 9, and 3, 2 for you to use.
Yes. And then it will. So according to this, for this example, it is working out.
Yeah.
I'm just thinking whether it will work out in all cases.
I mean, this is of course brute force.
Yeah. Well, not exactly brute force, because you're doing some, you're sorting it and then you're making some decisions, right?
Yeah.
Brute force would have been you check all possibility, 8, 6, 8, 9, 9, 7, 6, 7. Yeah.
Yeah. So the sorting itself will be like n log n. I don't think we are using any process that's more time complex than n log n. So perhaps this is n log n. I don't know. N log n plus n. So n log n.
Sir,
Yeah,
I think if we use this method, then there could be a case that suppose we have two, like we have 7, 1 and 6, 2. We have two cases which are making differences by huge difference, like all other are making 1 and 1, and these are making 4 and 6. Suppose we have these two and we have same like 8, 9 or 2, 3, which are making very less difference. But if there is some kind of number where if we move, if every pair is making an average of 4 difference.
Okay.
But if you go by greedy, then it will neglect those the averages add up to the more than the difference is making by 2 greedy. The first we have chosen the greedy. Suppose if there is 9, 7 and 9, 7 and 7, 1, if there were more difference in 9, 7.
Yeah. And another, maybe related to that was, for example, this is 7, 1, 6. For example, if this was 6, 0. No, sorry, not 6, 0. Suppose if this was 6, 2. No, so which would you, 7, 1 was the maximum, right? 7, 1 is this. Now, if you have something like, suppose if this was also 1. Yeah, now in this case, which will you choose?
In this case, the 7, first we will choose 7, 1.
No, like should we choose this or should we choose this?
Yeah, that's.
In that case, we'll be choosing the 8, 1, sir, because that would give the highest difference in this approach.
Yeah, no, I'm saying, let's take this as some 2 or something, just for the example. 2, and this is also, let's say, 3 or something. My question is, in the maximum itself, if we, and the configuration is like this, one is vertical and one is horizontal, which should we choose?
Now there is a problem, because if we choose any, then if we choose the vertical or horizontal, we don't know what will be the other maximum.
Yeah. So in case of ties, in the maximum case, we don't know which to choose, right? And that might, so this is giving an indication that just a greedy strategy is not working.
There is one question.
Yeah.
We do have to select all the tiles. We should have to cover all the numbers, or
yes,
we can left some.
No, you have to cover all the tiles.
All the, okay.
All right, good. So this is how you should actually solve problem. I mean, especially if you're thinking of a greedy approach, try to see if it works. Think of counter examples. So for this, what I've tried out and what works is you can use the dynamic programming approach because you really don't know which to choose, right? So at each step, you can either choose one vertical, right, and calculate the score, or you choose two horizontals, calculate the score, store it somewhere, right? In the next step, if you have chosen the vertical, either choose a vertical, the next one as vertical, or two horizontals. And if you have chosen two horizontals, I can either choose one vertical or two horizontals. So keep on following this, and at each step, try to find the score, right? And by the time you reach the end, right, you will get a score. Choose the maximum. You will get a set of scores. Choose the maximum and return that. All right. Yeah, I think this is a good place to close. Unless, yeah, so you can try the dynamic programming approach here. All right. Yeah. So regarding sessions, I just had a word with Atul. So yeah, this is the last session for this week. Next week we'll be having revision sessions. So since this was just like week 12 and we didn't have any new content covered, so we'll just have this one session for this week. Next week we will be having revision sessions as well, right? Okay. So go through these programming questions. I think it will definitely help you for the OPP, right? And yeah, so all the best. We'll meet again next week. Okay, everyone. See you. Bye.
Sure.
Yeah. Any other doubts? Okay. Chalo. Bye. Bye.
Thank you, sir.
All right. Bye.